Here if you observe, this is IDSS, right? So how to find the value of IDSS? And this curve looks like a parabola. Okay, so the expression for this curve will be something like this: ID is equal to k times of VGS minus VGS threshold whole square. Okay, this is a parabolic curve, that's why we are taking like this expression. Okay, so on differentiating this you will get like this. Okay, so for D MOSFET characteristics, ID is equal to IDSS1, VGS is equal to 0, that is this one. When VGS equal to 0, when VGS is equal to 0, ID equal to IDSS. Okay, so that I am substituting here, then ID become IDSS, that equal to K into VGS is 0 minus VTH whole square. Okay, so now if I substitute this K value in this, I will get like this. Okay, finally the expression is ID is equal to IDSS into 1 minus VGS threshold by VG whole square. So from this we can obtain IDSS value. Okay, we are measuring ID value, right? VGS for a given device, it is specified in the data sheet. Okay, VGS we can measure. So from that we can measure IDSS. Okay, now MOSFET acts as a switch. How MOSFET acts as a switch? See, this is a enhancement MOSFET. If you give, so this is zero voltage. If you tie like this is also zero voltage. Means we are not applying any gate voltage. Okay, I am repeating. This is zero voltage. I am giving a connection like this means VG is VGS is 0. 0 VGS means it won't conduct. Okay. Now this is something like this. It resembles like this. Means whatever the voltage is appeared here. Okay. Because this is open circuit, no current flows. Okay. As no current flows through this, there is no drop in this resistance. I into RL is 0. So whatever VDD is applied at the V out. Okay, so under open switch condition it is like this. If you take a closed switch, means I am connecting this V into this, so VDD is applied here, so maximum voltage applied at the gate. Then what happens? So channel opens. Okay, it starts conducting, so some current flows from here to here. It's a closed switch. As now current flows from here to here, there is some drop in RL and V out is minimum. Here V out is maximum, here V out is very minimum. It acts as a closed switch. So applied voltage at the gate terminal is maximum. Okay, this makes the channel resistance become so small. Channel resistance is so small, so maximum saturation current flows. So this is called saturation mode, and in this mode MOSFET is completely turned on as an on switch. Okay, here this acts as a on switch, this acts as a off switch. If you want to turn off, you have to apply this one. If you want to turn on, you have to apply this one. Okay, turn off switch means this one, on switch means this one. Okay, how this work as an on switch and off switch? For clear understanding, see this one. Okay, let us suppose we are connecting the so-called output what we discussed earlier somewhere here. Okay, this is the output. Okay, this is the output what we are mentioned here V out, let us suppose. Okay, this is the V out. Okay, now if I turn on this switch, what happen? This 5 volt is connected to here, maximum gate voltage, channel opens, so sorry, channel closes and the current flows like this, and this LED glows. This is on switch. If I turn off this one, it's a push button. If I turn off this one, no voltage applied to this, then what happen? No voltage here, so channel will not conduct, no current flows from here to here. Okay, so voltage appeared at this point is V out, but this is opened. Okay, so this won't glow, that is off switch. Okay, when you turn on this one, this 5 volt appeared here, this LED glows on switch. If you turn off this one, this 5 volt will not apply to this, and this is opened and no current flows through this. This acts as off switch, as simple as that. Okay, I hope you understand what is how this MOSFET acts as a switch also. Okay, see a small numerical example. 6 volts is applied 24 watts when it is fully on. Okay, so P is the power input, V into ID. ID is equal to input power by voltage, this much, that is I square, and PD, that is power loss, is nothing but I square into RDS. RDS means this is resistance of the channel. Okay, when conducting, you have to consider channel resistance, not drain resistance or source resistance. So here RD, here RS, but we need RDS. Why? Because this device is conducting, so we have to consider device conduction losses, RDS. That's why we keep RDS here. ID means whatever the drain current, that is only flowing like this, right? When it is conducting, this ID into ID square RDS is losses. That is 1.6 watts. So what is the power input? V into ID. Here we are applying some 6 volts, let us suppose, in the numerical example, and the current obtaining is the power input. If you give 24 watt power, 24 watt power source is there, then it is drawing some current of 6 watt, means not power source, actually then 24 watt lamp. Okay, so whatever the LED, not LED here, let us suppose we are connecting some 24 watt bulb. Okay, so based on the load only it will draw load current, right? It is 24 watt bulb. Okay, I am giving a 6 volt input. How much current it will draw? 24 by 6. Okay, that is 4 amps. So the MOSFET conduction losses are this much, 1.6 watts. Okay, if you use a on off switch, that is manually on off switch, then also we can make the bulb operate. But if you use a MOSFET, what are the losses? Means this much, 1.6 watt, and it is almost 5 to 6% of the total power drawn by the bulb. Okay, so power drawn by the bulb is this much, 24 watts, and loss in the switch is 1.6 watt only. Okay, if you want to further reduce this losses, means one way is to reduce this ID current or RDS by in by doing some modifications in the manufacturing by reducing the channel losses. Okay, thank you.